Welcome back to the Physics Almanac. In this video, I'm going to be proving Kepler's third law using Newton's laws of motion and his law of gravitation. And we're going to see that Kepler's third law, as he stated, is not exactly correct. In the process, we're also going to be deriving Kepler's equation. I've rated the physics level in this video as advanced. We are going to have to do a little bit of calculus. Let's first remind ourselves what exactly Kepler's third law states. It says that a planet's orbital period squared is proportional to its semi-major axis cubed. So you may recall from the first law, planets go around the sun in ellipses, with the sun at the focus of the ellipse. The semi-major axis of an ellipse is half of the longest axis. So what the law says, the time it takes to go all the way around, complete one revolution, which I've called p here for the period, if you square it, it will be proportional to the semi-major axis cubed. This gives us a relationship between the period and the distance of a planet from the sun. If you know the period, you can figure out the size of its orbit. Now, this is not actually how Kepler stated his third law. Instead of the semi-major axis, he stated it as the mean distance cubed. And we're going to see by the end of the video that the semi-major axis and the mean distance are not exactly the same. So now let's see if we can derive this law. What we need to figure out is the period, meaning how does the orbit depend on time? We already know from the first law that the orbit is an ellipse with the sun at a focus. An ellipse has two axes, the major axis and the minor axis, and half the major axis I'm going to call A, and half the minor axis I'm going to call B. These are generally called the semi-major and semi-minor axes. The first law states that we then place the sun at a focus. The distance from the center of the ellipse to the focus is A times the eccentricity. If the eccentricity is 0, then the focus is at the center of the ellipse and the ellipse is a circle. The planet will then orbit the sun along this ellipse. And the position of the planet relative to the sun I'm going to call r. R is a vector. It has a length and a direction. And we're going to take our starting point to be the nearest approach to the sun, called the perihelion point, meaning our angular position phi is going to be measured relative to the perihelion position. You don't have to do this, it doesn't really make a difference. We have to pick a starting point somewhere, so we'll just pick the perihelion point. Given this setup, I showed in an earlier video when I derived Kepler's first law that the distance from the sun to the planet had the following equation. But this is the distance as a function of phi, the angular position. What we want is the angular position as a function of time. And we're going to use Kepler's first two laws to try to figure this out. From the second law, we know that the time elapsed is proportional to the area swept out by this vector r. So the time it will take for the planet to go from the starting position to whatever position it's at will be proportional to the area this vector r swept out from that starting position, so this little somewhat triangular shaped chunk of the ellipse. And this turned out to be a consequence of conservation of angular momentum, which we found in the process of deriving the first law. Little l is the angular momentum divided by the mass, and it's conserved. It's a constant of motion. Substituting that in, we get that dt is r squared d phi over L, or 2 over L dA. Now, Kepler, when he came up with his second law, doesn't know about conservation of angular momentum. He just knows dt is proportional to dA, but he doesn't know what this constant of proportionality is. But we do, thanks to Newton's laws. When we derived the first law, we found that L squared over gm equaled the minimum radius, so the distance at perihelion, times 1 plus e. M here is the total mass of the system, meaning the mass of the sun plus the planet. But the sun is much more massive than all the planets, so it's essentially just the mass of the sun. And the minimum radius, being the distance of perihelion, we can see from this line right here is going to be A minus AE. So it's A times 1 minus E, giving us that L squared over gm equals A times 1 minus E squared. So we know this, but Kepler doesn't. Now we can plug in our equation for r into this equation relating dt and dA. I should point out here, dt and dA in this case are taken to be very small increments of time and area. In fact, infinitesimally small. Again, this is calculus. Kepler doesn't know about calculus, but he still is capable of thinking in small quantities, just not quite to the level of calculus. Okay, so plugging r into this equation, we get the following expression for dt as a function of phi. Now we have what we want, an equation that relates time to the angular position. All we gotta do is integrate this. Well, you could just plug this into Mathematica and get the answer, but actually, if you do that, you're going to get a very complicated expression. If you're finding this video helpful so far, please take a second to like and subscribe, and please consider checking out my Ko-fi page, where you can support the channel for as little as $5. There'll be a link to it at the end of the video. It can also be found in the video description. This is actually a case where using Mathematica makes your life more difficult. If you do this by hand and use a little cleverness, you can actually get a much more simplified equation. So we're not going to use Mathematica. We're going to use Kepler's method, at least in part. Kepler didn't do calculus, but Kepler had to solve this, and he did. But Kepler solved this using geometry. First, he imagined, let's inscribe this ellipse inside of a circle. This circle has a radius of a. And now we're going to drop a vertical from the circle going through the position of the planet. And we're going to draw a line from the center of the ellipse, which is also the center of the circle, to that position on the circle. Notice that no matter the position of the planet, this line has a length a. And now, instead of thinking in terms of phi, we're going to think in terms of this angle, theta. Now, I want to clarify something here. Theta is not the position the planet would have were it to have a circular orbit. And we're going to see why at the end of this video. Now we have to relate theta to phi. So let's take a look at this yellow triangle. This horizontal component here is adjacent to theta, so it's going to be equal to a times cosine theta. But that's also going to be equal to AE plus this horizontal component of our initial triangle involving the angle phi. So that's going to be equal to AE plus r cosine theta. R depends on phi, and it's equal to this quantity inside these square brackets. So let's substitute that in. And now we can rearrange this. I'll spare you the algebra, but I encourage you to check for yourself to get cosine phi as a function of theta. Now that we know cosine phi, we can easily find sine phi by using the relationship that sine squared plus cosine squared equals 1. But actually what we want is 1 plus e cosine phi, and then we got to figure out what d phi is. 1 plus e cosine phi, again I'm going to spare you the algebra, will be equal to 1 minus e squared over 1 minus e cosine theta. Now we have to figure out d phi. That's going to be a little bit more work. What we're going to do is we're going to differentiate both sides of this equation relating cosine phi to theta. The derivative of cosine phi is going to be negative sine phi d phi, and that's going to be equal to the differential of this entire quantity, which you can find by using the quotient rule for differentiation. Again, I'm going to spare you the algebra, but I encourage you to work it out for yourself. And when you do that, you can then plug in what sine phi is in terms of theta, and get that d phi equals square root of 1 minus e squared over 1 minus e cosine theta times d theta. We can now plug these two yellow equations into our expression for dt. This may look a little scary, but actually we're going to get some nice cancellations. We have a 1 minus e squared squared on the top and the bottom, so they cancel. And then we can cancel one of these 1 minus e cosine thetas, giving us this much simpler expression for dt. So after all this work, we've got this much simpler equation to integrate. Before we do that, I just want to point out that the area of an ellipse is pi AB, which is equal to pi a squared times the square root of 1 minus e squared, which is in fact almost what we have up here. So this constant term in front of our integral is actually equal to a over pi L. And I'm just going to call that whole thing k. And the reason I'm going to call that is because Kepler doesn't know what L is. Plus, he doesn't know about calculus, so he can't integrate this. He instead solved it geometrically using arguments involving the ratios of the area inside the blue circle versus inside the green ellipse. So without calculus, he managed to solve this purely geometrically. But we know about calculus, so we're just going to integrate both sides of this equation. This is a very simple integral now. The left-hand side is just going to give us time, And the right-hand side, well, the integral of 1 is just theta, and the integral of cosine theta is sine theta. So we get time equals a constant times theta minus e sine theta. Kepler had to figure out what this constant was. Well, if you plug in 2 pi, you've gone all the way around, so that should be the period. And sine of 2 pi is 0, so we're going to have that the period is equal to k times 2 pi. So k is the period divided by 2 pi, and the period over 2 pi is 1 over the frequency. In this case, it would be the average frequency, which is the frequency of the circular orbit. So we can now rewrite our equation as omega t equals theta minus e sine theta. And this is known as the Kepler equation. And Kepler struggled to invert this equation to get theta as a function of time. We then know how to get from theta back to phi. The problem is this equation cannot be inverted. This is a transcendental equation. There is no way to get theta as a function of time, and therefore phi as a function of time. But that's okay, at least we have time as a function of theta. And this is why I pointed out earlier that this yellow position on our circle is not the position that the planet would have were it to have a circular orbit. Because were the planet to have a circular orbit, the angular position would be omega t. And this angular position is theta, and we can see that omega t is slightly less than theta, at least if you're on this side of the ellipse. Once sine theta goes negative, meaning down here, then omega t is going to be ahead of theta. And that's because the planet moves faster when it's closer to the sun. So initially, the circular orbit lags behind the planet on the ellipse, but then catches up by the time you get to the exact other side, meaning aphelion, the furthest point away from the sun. That will correspond to theta equals pi, and sine of pi is 0, so here we would have omega t equals theta. So they meet up again at this point, and then the planet along the ellipse will lag behind and eventually catch up again by the time you get back to perihelion. Since we know k, we can now use that to prove Kepler's third law. Now you might be wondering, if Kepler didn't know k, if all he knew was that it was related to the period, how did he figure out the third law? Well, he actually guessed it by trial and error. He guessed that the orbits should follow musical theory, specifically musical harmonics. So he guessed that the period raised to some exponent should be proportional to the average distance raised to another exponent. And basically he just tried plugging in numbers and compared to his data until he figured out that if n equals 2 and m equals 3, it works. So Kepler figures it out empirically, but thanks to Newton, we can actually derive it since we know k and we know L. So we can just plug everything into p equals 2 pi k, and simplifying, we get the period is proportional to 2 pi times the square root of a cubed over gm. We can now square everything to get p squared is proportional to a cubed. Now we're not quite done yet, because at the very beginning of this video, I had told you that Kepler's third law, the way he stated it, did not say p squared is proportional to a cubed, but proportional to the average distance cubed. Well, what is the average distance cubed? Well, it kind of depends what you mean by average, and I'm not sure exactly what Kepler meant. Did he mean the geometric average, meaning just the average distance of an ellipse? That would be the angular average, if you want to call it that. Or did he mean the time average? Since the planet doesn't move at a constant speed along the ellipse, those two numbers are different. And if you work out what those are, they're not equal to A. The geometric average is actually equal to B, the semi-minor axis. So I'm guessing Kepler probably meant the time average, because he was a very advanced mathematician and had a full understanding of the geometry of ellipses. And if this is what he meant by average, he probably would have stated his law as p squared is proportional to b cubed. If instead you work out the time average distance, it's slightly more than a, and depends on the eccentricity. But all the planets have very small eccentricities, and so the eccentricity squared is a really small number, so it's basically a, which also means that b is also basically a. So when he compared to his data, this extra factor of e squared was probably negligible. But we know today that it's actually a cubed, not the average distance cubed. So today, Kepler's third law is stated as p squared is proportional to a cubed. And there we have it. We've now derived Kepler's third law, In the next video, we'll be taking a look at other properties of orbital motion, specifically conservation of energy and angular momentum. So if you found this video helpful, be sure to like and subscribe and hit the bell to be notified for the release of future physics videos. And if you'd like to support the channel, you can go to my Ko-fi page, or you can just leave a super thanks. Thanks for watching, and I'll see you in the next one.